numbers, and we didn't go too much into details, but there are a couple of issues which I hope you remember, and those are essential. The first one is that we need a positional system, because if you don't have a positional system, you cannot really process the numbers in a very nice way. If you deal with Roman numerals, which is not positional, you cannot operate on digits which are on the same way. A positional system is helping you to do that. Second was about the sign. And we went through the possible representations of sign numbers, and we stopped at this 2's complement stuff. And I would like to revisit it a bit. Then essentially, when you design a system, you know your dynamic range. Then you will not be able to represent numbers which are beyond that dynamic range. Then if you have a 16-bit architecture, you can represent numbers which are within those 16-bit. Then 2 to the power 16 possible combinations, right? Now, if you want to represent positive and negative numbers as well, in general, you say, okay, I want to represent n negative numbers, I want to represent p positive numbers, and I want to represent also 0. Then I will need a number m, which is my modulus, which is larger or equal with this. Because otherwise, I will not have enough capacity to represent numbers. In such a system, if I have x and I want to compute minus x is equal with m minus x. Then I would say I have to make a subtraction in order to compute minus x, to change the sign. Now, this is not brilliant if that subtraction is a real one. However, nobody is forcing me to choose an m which is of random value. Then if I choose an m which has some interesting properties, and those properties are to be a power of 2 or to be a power of 2 minus 1, this subtraction can be actually got for free, or almost for free. The reason for that, we discuss it. We discuss it here, that if I compute m minus x, I can play some tricks, some small arithmetic, and this will end up in me doing a complement of x and to add a unit in last position. I say that 2 to the power k minus unit in last position, it's always a string of 1. Let us assume I have 3 bits, and then my complement will be 8, right? Because here I have between 0 and 7 possibilities. I am trying to play this game, then my complement is 2 to the power k, which is 2 to the power 3, which is 8. Now 8 is this representation, right? 8 minus 1 is 1, 1, 1. And this holds true whatever the value is, only for 2 to the power k, for sure. Now, if I subtract something from 1, 1, 1, I will never get any carry, because what I subtract from here, it's either a 0 or a 1. If it is a 0, I will copy it. If it is a 1, will be a 0, the result of the subtraction. Which means I can do that subtraction on all the bits in parallel, with no carry between positions, and it's just a complementation. And that's the beauty of using 2's complement with a complement which is a power of 2. Now, the other complementation is when you say, I want 2 to the power k minus 1. Then I already have a complement which is 1, 1, 1, 1. Then my calculation for minus x, it's only the complementation. You look at me like I don't know, how should I tell it? You understand everything is crystal clear, or it's like, you know, what is he talking about? Basically, the one's complement looks to be nicer, right? Because I don't have the extra unit in last position, which I should do something with it. But there is a reason why, in practice, in computers, we don't use one's complement. We mostly use two's complement, and that you will see in just a sec. Now, that was a kind of recapitulation of what we were discussing last time, highlighting the main points, right? Positional systems and complement representation, and the beauty of those kind of radix complement and digit complement. Now there are extra things here. In practice, you may have operands which are not spreading on the same number of bits or digits. And in order to do good calculations, you have to extend them. Let's say I get from a digital to analog converter, I get values which are on 6 bits. My architecture is working on 8 bits. I have to do something with those bits in order to be well aligned. Then in my computer I have some constants which are on 8 bits. I do the measurements on 6 bits, and then if I'm not doing what I should, I will add apples and pears, and I will not get the right result. Now, this will not matter if you deal with unsigned numbers. But when you deal with signed numbers, you have to treat the sign in a different way. Because if you don't do that, you will not get the right result. Let's say this is 1, 0, 0. No, 1, 0, 1. I don't know why I like this. If this is an unsigned number, it's a 5, right? If it is a 2's complement number, it is a -3. Now I have another number, which is a constant in my system, which is again negative. Let's say it's this one. That's my representation in my computer. And this is -8, right? If I try to do something to add them in this way, my result will not be correct. You can try and you will see it won't be correct. What you have to do is you have to deal with the sign. Here is the sign bit, here is the sign bit. They are not in the same position. And what I have to do two things. To put things which do contribute in the same way in the same position, and to preserve the value. Because this should be a -8, and this should be a -3. And the way I'm doing it is very simple. For 2's complement numbers, I'm just padding them with a copy of the sign bit. If I put here a 1, this is a -3. If I put here another one, it's still a -3. And I put my 1's here forever. The value will be preserved, and I will extend it enough. Okay, my extension was until this point. If I have fractional numbers, what I have to do on the fractional part, let's say, okay, I have the sign here, okay, and this one has a 1 in this place. In order to solve this problem, to add them, I will pad here with zeros. This is different for 1's complement representation, okay? Now, as you will see later, this kind of things should be treated with care when you do multiplication and addition. Sign extension is one way to deal with that. There are other things which are possible also in order to make it more effective, but we'll revisit that. Now, a part of the sign extension, when you do complement calculation, you have an extra ingredient. Doesn't matter what your result is, it always has to be modulo m. Then if I process to numbers, the result cannot be larger than my m. It doesn't make sense. This is my system. Whatever is going out, it should be brought back modulo m. Now, modulo m calculation in general is difficult. However, if you do arithmetic in 2's complement, then modulo 2 at power k, modulo m is trivial. Why is that? Because you just drop the carry out. Okay, I hope you all know what modulo operation is, right? Yes, no, maybe?
Yes.
Yes. Okay. Are you sure? Once, twice? Okay, then I'll not explain. I'm happy. The less I work, the better it is, right? I save energy. I operate on batteries for now. Okay, now when I do a calculation in digit complement, then 1's complement in our case, there is a problem because while modulo 2 at power k was simple, then I was operating on 3 bits. Okay? Now, if my result will produce here something out, I just drop it. Because it doesn't make sense. I cannot have numbers which are larger than 8. Then my result should be in that domain. Now, if I do modulo 2 at power k minus 1, that modulo operation is a bit more complicated. And the way we do it is like that. There is a typo here in the slide. Here should be a plus. Yeah, you see, I'm adding two numbers, and if the number is too large, I have to subtract 2 at power k minus 1. It doesn't mean that modulo calculation is always done by subtraction. I'm subtracting that modulo because I'm adding two numbers, and the result cannot be larger, that cannot embed more than one modulo value in it. If I multiply two numbers, then the result can be a lot larger, and then I have to do a division. In here, one subtraction will be enough. And what I'm doing the following. I'm subtracting 2 at power k, which it's a bit too much, yes?
Another room joint.
Another room.
Okay, but it's an empty room.
But it's a room.
It's a room, yeah, sure. Thank you for letting me know. Then I am subtracting 2 at power k, but this is 1 unit too much. And in order to compensate for my, enthusiasm, I will have to add a unit in last position to get the right result. Now, what you see already is that doesn't matter how you play, there is a kind of penalty. If you do 2's complement, you do a complementation and you have to add a unit in last position in order to obtain the number. But when you do modulo, you just drop the carry out. When you do 1's complement, when you compute the minus value, you just do complementation and no headache with the unit in last position. However, when you do the addition in 1's complement, you have to deal with that addition. Then somehow, there is no way out. This is, in engineering, this is a kind of misery that some problems do have a certain complexity and there is no way to simplify it. A smart approach is to move that complexity in places where you can deal with it in a better way. That's the way we do smart things in engineering. Okay. Now, in here it's a table which is, comparing the two complement representation, about symmetry, about having a unit 0, and about how you do complementation and how you do modulo addition. And you see what I just told you. For 2's complement, add a unit, no problem in here, and in here drop the carry out, but here you have another problem. Okay, we've been into this thing last time. This is a two's complement header, and it's a comparison between the two of them. Now, this is an approach which is more general. Then this is giving us an overview on how can we deal with the sign in general. There are two strategies. I can deal with the sign in a direct way. Then I take the numbers with sign inside, and I'm producing a number which is a result, which is taking that into consideration in the calculation. And this is two's complement, one's complement approach. Or I can do a separation between sign and magnitude. And this is how sign and magnitude is working. And this is working in general. Now, which one do you think is better?
General. General.
The general. Both of them are general. But one is treating the sign in the same package. The other one is making a separation. I have a problem, I split it in two, and then I treat each problem in a different way, and I combine and obtain the solution. Which one do you think is better? This one or this one? Now you are thinking, why are you asking us that many questions? We are sleeping still. Or not?
No.
Oh, come on, make a guess.
I think the first one.
The first one,
That's the upper.
this one.
Yes. You need only one part of upper. So
Yeah, but you also have to see what's inside the hardware,
yeah,
right?
that's
No, as usual, my questions are traps. Okay, there is no good answer for that. You are right in the sense that when I deal with addition, which is a fundamental operation, I should better try to find a good solution in this way. But in complex cases, when this approach, which is splitting a large problem into two different problems, which I solve separately, and then I combine the result, it's good to deal with complexity. That sometimes this is better, sometimes this is better. For addition, that's the choice. For other things, this might be a choice, you know. This is a general strategy in solving problems. Probably you learned about it with the name of divide and conquer, right? But the proper name should be divide et impera. You know why?
It's in Latin.
Sorry?
It's in Latin.
It's in Latin, but why should be divide et impera?
Because the Romans.
Because the Romans invented that in politics, you know, and in military management. We are using that concept in science, but they invent it with a different purpose. Okay. Now, there is something which I didn't say anything about, but somehow I use it when I made my guess about the values of numbers in two's complement notation in a very simple way. Then what we are saying is that each digit has a weight. And thus far we are saying, or for unsigned numbers, the weight, it's always positive. Now, a way to understand fast the value of a signed number is to think in this way, that all the positions which refer to the value, except the most significant bit, do have positive weights. The one which refers to the sign or the most significant position has a negative weight. And by treating that, I can see very fast the value of the number. Okay? When I was here, I don't know where, I was looking at this 1000, and I said, this is -8. Because this is, I have 1 here, and this is 1 times 2 at power 3 with minus, and the rest are 0. Then it's -8. you can see here an explanation of why this is correct. You know, you take x, you apply the complementation. This is in 2's complement. Then you do the complementation of things. Because you add here a hot one, this part will change. And you see after calculation that this is indeed 90. This is very simple and it's good for us, for humans, to understand what we are doing and to understand numbers. Inside the computer doesn't matter. But this is opening a kind of new avenue in dealing with the sign. Because what we had a sign for the number in general, and now I have a sign for the weight. And thus far, all the sign information was in the sign of the number. I can also have digits which are positive or negative. Then I can embed the sign in the digits, okay? Now, I have here an example, you know, I have a radix for representation, and instead of for radix for representation, the standard digit set will be 0, 1, 2, 3. In the same way as for radix 2, the standard set is 0, 1. Then in radix R, the general digit set is 0, 1, 2, whatever until R minus 1. If I conserve the number of digits, I can embed some sign information in the digit 2. And I can make a different representation of a number, assuming now a digit set in minus 1, 0, 1, 2. Then I have sign in the digit, and it's also redundant, because I have more than the digits that I had before, okay? Now, how do I make a conversion between those? This is a fundamental concept in dealing with sign in digit and in changing the radix and in doing what is called totally parallel addition. I have a digit, my number is 3112023, and this is valid in my initial representation, but my target will be to have this represented in the same radix, but now with digits between minus 1 and 2. The first position is a 3. 3 cannot be represented in my new digit set. However, I can do a trick. I can write 3 as being 4 minus 1. I didn't do anything wrong. I'm conserving the value, do I? And then this means that I will write 3 as minus 1 in here, and 4, which means a carry into the next position. Did you get it? No. 3. I write it as 4 minus 1. This is radix 4 notation. Then the weight of this column, it's 4 at power 0. The weight of this column is 4 at power 1. Then a carry in here, a 1 here, will contribute to the total value of the number with 4. And then this is 4 minus 1, which is 3. And I'm conserving the value. And not only that I'm conserving the value, I solve my problem for the first digit, which is not any longer 3, is now a minus 1, which is in my target. And I can continue rewriting all the digits in this way, which means I have now some values which are my digits, and I also have some transfers to the next position.
Sorry, a question.
Yes?
Question, can you use your mouse to point to the slide?
I was not pointing to the slides. I know what you want. I was just talking about the slides. I was not pointing.
Okay.
But I will try to point. I don't like that because you keep me here stuck close to the laptop. And I like to move around. I'm playing a theater here. No, actually teaching a class, it's like theater. Okay? Then I managed to rewrite this as 4 minus 1. 2, it's a legitimate digit, no problem, I can copy it. 0, it's okay, this is okay, this is okay, this I'll do it again. Now what I obtain are some digits and some transfers. And if I sum them up in order to get the right result, I obtain this, which is still not good, because 2 plus 1 will give me here a 3. And I have to do the same trick again. I will rewrite this, and then after 2 steps of rewriting, I get the result. Now, this is a conversion, can be done also in hardware, not only as I explained you, and can be done in parallel, because I inspect each digit one at a time, you know, but not sequential. What I see is that I need 2 steps of conversion. And I don't really like that. I would like somehow to do that conversion in a fixed amount of time, in a predictive way. Because if I would not have had the 2 in here in the second position, okay, I could get the result directly. Now, what I don't like is the fact that I get here a 1 plus a 2. There is no way to rewrite this in a different way, and there is no way to rewrite these 2 in a nicer way which will solve my problem. Because 2, it's even 2, or it's 4 minus 2. I can write it as a 4 minus 2, but I don't have a minus 2. Then I don't have a solution in this digit set to solve this problem without having a number of iterations. Sometimes I'm lucky and I get the result in 1 iteration. Other times, you know, I'm not that lucky and I have to iterate. In practice, what I like is to do that in 1 shot, and I can do that if I have redundancy in the digit set. Okay, this is a, yes?
Sorry, Bruce, like that. So the idea is that we don't propagate a carry.
The idea is to stop the propagation of the carry in this process, and also the idea is essentially to get the right digit values. And in here, because I have 2 plus 1, I obtain again a 3, which is not valid. Now, I can solve that problem if I change the digit set and I allow for a bit of redundancy. Then instead of having minus 1, 2, I put now minus 2, 2. This will not be for free, you know. I mean, when I do an implementation in hardware, I also have to think about the consequences of that. But now we are concentrating on the concepts. Now, because I have that choice, I could solve my problem. Then I don't have to change this 2 because it's a legitimate digit. However, if I look back over my shoulder, I see that the transfer is coming and I can, you know, predict that transfer, or I can really compute it. And because I see the transfer, I will say, no, 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 I won't leave 2 as it is. I will write it as 4 minus 2. Then I will generate a transfer here and a minus 2 here. The rest is the same. I can apply the same principle here, but I don't have to. You see? In here I did the same just because I wanted to show you that I may or may not do it. In here I have to do this transformation. In here I could leave it as it is because it won't be a problem. There is no transfer from the previous case. Then right now I get always the conversion in 1 iteration step because I have that choice. What I have to do is I have to look behind, okay, and do what is called look ahead. It's strange because you don't look ahead, you just look behind, you know, on the previous digit. But it's called look ahead because you do a prediction. You have 2 possibilities. One is to say, I'm waiting for the previous digit to compute. I see if there is a transfer, and if there is a transfer, I make the right choice. This is slow, I don't like it. You know, you all like fast computers. To have fast computer, you have to have parallelism. And parallelism is starting at this level, at bit parallelism. It's going to instruction parallelism, thread parallelism, task parallelism, applications parallelism, you know all those. But the smallest granularity, it's at the bit level. Okay. Are we clear with this rewriting technique? Okay. Now remember the notation with the dots, because we know some more things now about the digit and the sign of the digit. We can use notations which are telling us about the weight of a certain position. The first line is unsigned. The second one is 2's complement. Remember, the most significant digit has a negative weight. The last one is a negative radix. Odd powers do have a negative weight. And I can represent numbers in a negative radix as well. Nobody precludes me to do that. We don't do that in general cases, but we can. If we have to, the same will apply now for addition and multiplication, where I have the negative things. I see now, and this is creating a problem, that in multiplication, due to the fact that this has a negative weight and this has a negative weight, the dots which are on the diagonal and on the last row, except for the last one, are having negative weights. And I have now, when I do multiplication, I have to deal with that in a proper way. Because when I'm adding this column to obtain this result, some carry is coming from here as well. These are contributed in a positive way and these are in a negative way, which is making my life miserable. But there are solutions for that. And we'll talk about those. There is always a kind of circle in introducing a new material. There are things in the future which I need to explain the present. I have to cut it somehow. And it's interesting to speak about the numbers, the negative numbers in multiplication now in this context, but you should not try to understand everything, because we'll revisit the issue, don't worry. Now, our problem in computer arithmetic and in general in processors is called carry. No carry, it's paradise. However, there is no real way to avoid carry. Ideally, what I want is, if I have two numbers and I want to process them, I would like to process each digit pair in parallel with no interruption. But you remember when you do addition with pen and paper, you do on this column, there is a transfer, then you have to do serially. Now, how can I deal with that? Then one solution will be to say, okay, I'm adding them in parallel, and I'm not generating any transfer. Then here it's an example in radix 10. Then I can add them in parallel, you can see that. But now my digits did explode. Instead of having digits between 0 and 9, after one addition, my digits are going from 0 to 18. And you may say, okay, it's good. I got some advantage. I can do things in parallel. But what will happen when I do the next addition? And the next addition? Then this is not really a solution. Because if I let this happen, I have fully parallelism, but the numbers, the digit values are exploding, and they are essentially unlimited. No practical computer will be able to deal with that. You can use FPGA and you can reconfigure, your hardware, but you cannot reconfigure your hardware after each and every addition, and this is essentially unpractical. What you can do, however, is to do a kind of normalization. And in here, you see a normalization process. Then there is addition, you know, you have digits between 0 and 18. What you do is, in the first step, you do the addition of digits in parallel. As before, the values are too large, and then I have to make a conversion. And I do the conversion based on the same idea. I'm rewriting the digit as some kind of transfer to the next position and a value, a local value. Then I'm writing 36 as 20 plus 16. 16 will stay, okay, and 20 will come here as a transport of 2. This is power 10, right? 20 will be 10 plus 10. This will be 0 plus 20. Okay, then you see I have freedom to write numbers in the way I like and please within bounds, because my digit set is redundant. Now, if I do those transformations in a proper way, which means that after I rewrite these position sums in intermediate sum and transfers, and I make this final addition, if the maximum value that I can obtain here in an addition is 18, then I'm in business. Otherwise, I have a problem and my transformation was not correct. You see, I could also rewrite 36 as 6 plus 30. And no, that's not good. I don't have a bad example here. But assuming that here I had a 16, and here I write a 3, I get a value which is 19, and it's not correct. Then essentially, this is paving the way towards doing fast parallel addition. I allow digit extension for a while, then I have a step in which I'm taking the digits in parallel. Then this part, it's fully parallel. In here, there is no interaction. Then I am rewriting those as interim sum and transfers, which is another step which is done in parallel. There is no interaction. And if I do it in a proper way, when I do this addition, which is again going in parallel, there is no dependency of waiting from one position to the next position, I obtain the result within my initial digit set. Now, for that to work, I need to have redundant representation in order to be able to make choices. And I also have to look behind in order to see what kind of transfer is coming from the previous position, which essentially means that when I'm making here the rewriting, I have two approaches. I wait for this to be produced, but then I didn't solve any problem, because it will be slow, will be serial. Or instead of computing, rewriting this based on this value only, I assume these 4 numbers in this processing. Then I'm looking at my position, and I'm looking at the previous position, because only that position may give me something. And based on what I am and what my previous position is, I make the right choice. And then, you know, this guy has nobody behind, it's okay. This guy will take this 4, this guy will take this 4, this 4, this 4, this 4. Then, there is always a price to pay. But I win, because I have a parallel addition. All the steps are done in parallel. There is no sequence of operations. There is no serial processing. However, I have to look at my current position and whatever is behind me. Is that clear? To me, it's clear. I explained that many times. I even managed to understand it. Mm-hmm. It's clear, guys? It's okay, it's clear. If you want to ask something, just make noise.
Okay.
Then I can hear you, but I'm not looking at the TV monitor all the time. it's kind of difficult to split your attention. And it's also in a bad position, the monitor. It's on a side. According to me, it should be a bit towards the room, then I can see it too. But I'm trying to look at you also from time to time. I also see an empty room in Eindhoven, which looks brilliant. No, there is somebody there. Oh my God, but I cannot see you. I hope you can hear me at least and see the slides. Okay.
Yes, we can.
That's brilliant. You know, they made my day today. Hopefully things will go the same way. Okay, now, this is what I just explained you. The first approach is not possible because it's exploding the digit value. The second and the third approach are okay. Then you compute the position sum, you generate some transfer, and then you compute the final. This will require 2 steps. And you can also play that kind of things, you know, you increase your window over the operand and you do it faster. Now, again, I have a question. Don't have to hate me for that. Which one do you think is better? This one or this one? This one is not possible, but what will be your choice? Whew, suffering. Yes.
Depends on the length of the digit, how many digits you have. I would go for either the third one or the second one. It depends on
The
the
length
carry
of-
chain of the numbers.
Why? Because
Because you
I'm
have this-
processing numbers in parallel.
Yeah, but there is some serial connection. Let's say the carry.
No.
No.
This is exactly what I'm trying to cut.
Yeah, but I thought there are some partial.
No, there is nothing. I show you and then I'm processing this position and I'm generating a transfer which is coming here and no further than that position. And this one is not waiting for the transfer to come. If I use, oh, sorry guys. Sorry, I forgot about the constraints. Then I'm processing this position and this in parallel. This is producing a transfer to the next position, but only to the next position. There is no transfer further. Just let me finish. If this transfer would have contributed here, then I would have had a serial processing. However, even though the transfer is between 2 adjacent positions, it is coming in the right time for this, not to wait for it. That this is the beauty of the scheme, that there is talking between the positions, but nobody is waiting. Things are happening in parallel. Yes, your colleague had his priority.
Yeah, I have a question.
I had a question, then you first answered the question.
See.
Yes.
What if, for example, you look at Si plus 1
Si plus 1? Where?
let's say in the right one.
In this one, yes.
Yeah, what if it only generates a carry if that Si
I don't know.
gets a carry?
No, I don't know the value of Si, and there is no carry coming there.
No,
Then this box in here, it's assuming 4 inputs. The digits in my position and the digits in the previous position. Based on that 4 positions and the rules that we just discussed, is determining the output. And it's a deterministic way and there is no transfer.
yeah, that's the thing. I don't quite see yet why you don't have to look back even further.
Yeah.
Because of this, there is no way a transfer will go further than 1 position. Then if I get a transfer in this position, now okay, let's look here. If there is a transfer coming here, it may only come from this point. If it's coming from 2 positions behind, If my system is designed in such a way that it's coming from 2 positions behind, then I have to consider all 6 inputs. That can be done, but you know, this will create some extra things. Now, do you have you had some?
Yeah, well, about two-stage implementation on the next slide. Can the second stage of option B also produce a carry that
No.
has to be transferred? Or
No, because I just told you why.
It's based on the same
Based on the same information, you know, I'm making the right choice, and this depends on the redundancy in my digit set. If I don't have redundancy, I will have a problem. If I have redundancy, I have freedom, and I can solve it. But you did not answer my question. Yes.
I would choose for two-stage because I think it might be faster because the TI may not always play a role. It might not always be a carry going from one stage to the next.
Then your choice, it's probably my choice too, however, for different reasons. Then we speak about synchronous designs. Then in a processor, you don't, in a normal processor like you have in your mobile phone or in the laptop, things are going according to the conductor, which is the clock. And the clock is always coming for the worst case situation. Then the fact that I may have a transfer here or not will not really influence. I'll always assume that there is a transfer and I'll take it into the calculation. Now I will give you 1 more minute and then you may take a break. The reason why I choose the second and not the third relates to technology. Then for a theoretician, the choice is simple. Third one is the best. There are only 2 levels of processing in the circuit. Then I count, each box has a level. This has 1 level, this also has 1 level. Then this should be closer to what I would like to get. This has 2 levels. And theoretically speaking, 2 is larger than 1, which makes sense, right? However, this 1 level is more complex. And depending on the technology, this 1 level might be slower than 2 levels, which are simpler. Why is that?
Interconnection.
You remember concepts like gate fan-in?
Yes.
You should. The delay of a gate depends on the fan-in. While in here, my gates are taking 2 digits, in here I get 4 digits. And remember that those digits are not bits. They are values, let's say between 0 and 3. Then each digit is maybe 2 bits or 3 bits. Then the hardware will explode. Now, you can take a break, and I'll see you after the break.